In the previous video, we implemented the first search for a binary tree. Now, what we're going to do next is we're going to introduce a new edge, and that is this edge. And we are going to change the left child, right child representation to use an adjacency list instead. On introducing this edge, we don't really have an option because this is no longer a binary tree. We cannot represent all of these edges if we want to use the left child, right child representation. So we have to use some other representation for our edges. And we are going to use the adjacency list representation. So what we're going to do is we're going to maintain a list, which we are going to call ADJ to represent adjacency. And when we create a vertex object, we will have the list empty. Now, we will no longer be using the left and right children, so we can delete the left child and right child. Now, to set edges, once we're using adjacencies, what we're going to do is we are going to add the edges to the adjacency list. Now, we've got different options to do that. We could put a list here, and a better way is to show to Python that we are going to put a variable number of arguments for this method. And the way we do that in Python is we put an asterisk before a single name. Okay, so we're gonna call vertices. Now, when we do this, you're gonna notice both in Python as well as in lots of other programming languages like Java, what you do is now you treat this variable argument list name as if it was an array, or in Python, a list. Okay, so we're gonna say for vertex in vertexes, we are going to append the vertex. And that is pretty much it. Well, of course, we need to do changes here. Okay, now we still have Bob and Cass as neighbors of Abe, and we still have Dan as a neighbor of Bob. Okay, but now it doesn't make any sense to have none. And we were having none here because Bob did not have a left child. So we can remove that. And because this is taking a variable argument name, including one or no arguments, okay, or multiple arguments, we can have it this way. Also, the other thing we're going to do is, since we've added this additional edge, is we're going to indicate that edge. And that's it. Now we have to rewrite our depth first search algorithm because now we obviously don't have a left child and a right child. So what we're going to do is, instead of processing a left and a right child, we're going to process each item or each vertex that's on the adjacency list. Okay, now let's get this to run. Good. Okay, now let's see what's going on. What this algorithm says is we take a particular vertex and we go through all of the vertices that are in its set of adjacencies. We process them one at a time, and if any of those vertices has neighbors themselves or adjacencies themselves, we process those adjacencies at that time. So going through this and with this set of adjacencies that we've defined, we would expect at time point 1 to visit the first node, which is Abe, and then 2, 3, and then 4 for finish. And then at this point, we backtrack and get to 5. Now, up to this point, nothing strange. We should have been expecting this. Then, because we have this adjacency next, we get to treat it. So we go to 6, and then it doesn't have any adjacencies. Eve doesn't have any adjacencies on its list. So we go to 7, and once we're done with Eve, we go to the next vertex on Abe's list, which is Cas. So we go to 8 for first visit of Cas. But once we visit Cas, we would see that the first item on Cas's adjacency list is Eve. So that means from Cas, we're going to visit Eve, and this 6 is going to be updated to a 9. And then Eve doesn't have any adjacencies, so this 7, we're going to, it's the finish time, we're going to update it to 10. And then we're going to go to the next item on Cas's adjacencies list, which is flow, and we're going to visit it at time step 11 and finish time step 12. And then since we're done with all the adjacencies on Cas's list, we go back to Cas, backtracking, and give it time 12, 13, and then time 12, time step 14. Now, if you want to see if you actually do really understand how this works really well, one thing you could do is this. Exchange the position of VEve and VCAS on this list, and before running the code, try to see what the numbers would be, and then exchange the position of these two vertices, and then run the code and see what you will get, and if that matches what you thought you would get.